Welcome to day 2 of our challenge. Today we'll be talking about Poisson and negative binomial regression models. But let's get the basics first. When we think about Poisson regression models, the mental image we want to bring up is a chessboard, because we must be able to complete the following sentence: number of events per blank. So think of a Poisson model as being a chessboard where we have events occurring per square area or per block, right? So if you cannot think of your event in the context of events per something, where it could be events per area or number of events per whatever it is, that means that a Poisson model is not a good fit. The Poisson model assumes that the events are occurring at a uniform rate across the different squares, and that obviously each square is independent from the next. So what happens here does not influence the other person or the other square or area. Another very important assumption of Poisson models is that of equidispersion. In this picture here, think of the cover of the pot as being our variance and the pot itself as being the mean. So a Poisson model assumes that the cover and the pot are about the same, so that variance is about the same as the mean. Think of a scenario like this where you have number of people who visit a shop. Let's say that today you have 0 people attend or visit the shop. Tomorrow you have 5. Next tomorrow you have 10. So across all days, you see that the average number of people who come to that shop is about 5 people. Now, in this case, the variance is also about 5, because you're having jumps from 0, 5, 10. So in this case, mean is 5 and the variance is 5. So this is a case where we have equidispersion. Equi means equal. So in this case, the variance and the mean are about the same, and this is a perfect case where we'll need a Poisson model. In some cases, however, the assumption of equidispersion is violated. Here we have the variance does not cover the mean. You see the variance here is much smaller than the mean. This could occur in a scenario where in that same shop, for example, today you have 5 people attend the shop, tomorrow 4 people, next tomorrow you have 6. So across all days we have an average of 5, but the variance is 1, because from day to day you have changes of just 1 person. So in this case, the variance 1 is much smaller than the mean, which is 5. In this case, we cannot use a Poisson model. And then you have other cases where the variance is much larger than the mean. Think of a scenario like, let's go back to that same shop. Today you have 1 person, tomorrow you have 2 people, next tomorrow you have 0 people, and then during the Christmas periods or during major holidays, you have 300 people. The mean might still be 5 when you average across all 365 days in a year, but the jump, the variance, is quite dramatic in this case. So in this case, you have a scenario where the variance is much, much larger than the mean. So in these cases, we cannot use Poisson. So one of the major things we have to do or check off our list when we're trying to use count data or model count data is to empirically test for these assumptions. Do we have equidispersion, or is that assumption violated? We can only use Poisson when this assumption is met. Now let's go to our task for today and see how we can implement it on the Chi-Space platform. Our task for today is to analyze the same data from yesterday and look at the relationship between BMI category as the exposure and the number of cigarettes smoked per day. The theory here is that, well, changes in or differences in BMI class might influence smoking intensity. Perhaps individuals who are overweight or obese may want to smoke more cigarettes to lose weight. And so the question is this true? Now we're trying to adjust for potential confounders here. So first things first, we want to think about the assumptions. Before we even touch our analysis software to analyze data, we want to think of the number of cigarettes smoked across different types of smokers. Plus, is it plausible to expect that there is equidispersion. We might immediately think of hardened smokers who smoke a lot of cigarettes. And then we might also think on the lower end, we think of individuals who are, for example, new to smoking, or social smokers who might smoke way fewer number of cigarettes. So from just a common sense perspective, it might not be very plausible that there is equidispersion just by reasoning through it. So that's what we want to do at the very beginning. We want to think through the outcome and say, do we think it's reasonable to expect that the variance will be equal to the mean? And so we have our intuition very sharpened even before we look at any data. Now let's go ahead and fit the model in the chi-square platform and let's see how it performs. So we're fitting the number of cigarettes smoked per day as the outcome. It is a count variable, so it's appropriate. And so we'll go over to the platform and let's start a new project. We're going to call it day 2. I have provided a new data set which corrected for some of the problems with the variables from yesterday. So I'm going to share it. It's a parquet file, so I'm going to upload it here. So this is what you would expect. I think this is the file here. I'm going to import it. So I'm going to share that file with you. It has a correction to some of the variable names from yesterday, the names that ended with cat or categorical variables. Okay, so our data set is loading. All right, great. So we are not using weighted data, so we're going to say no to this. And let's quickly check to make sure our variables are here. The BMI cat is here. As you can see, it now has the labels properly appended. So you have obese, underweight, normal, and overweight. All right, that's our main exposure. Our primary outcome is number of cigarettes smoked per day, which is smoking intensity right here. And if we visualize that again to make sure that everything is fine. And so just by visualization, you can see that there's quite a skew to the number of cigarettes smoked. But let's go ahead and fit our Poisson model. We'll go to estimate, come to regression analysis. We'll select the model as a Poisson model. And now we can select our outcome variable as the number of cigarettes smoked per day, which is smoking intensity. We'll select our predictor variables. We have BMI cat, the BMI classification. You have chronic cough. I can't remember the exact variables, but so I'm just going to select a bunch of variables here just for demonstration purposes. You have sex, you have race, you have activity level, I believe, education, exercise levels, and we have also age. So let's stick with that. So we have our outcome selected, our predictors here. The primary exposure is BMI cat, and we are including these other variables as confounders. We can always check for test for confounding by looking at confounding analysis variables, but for now I'll just go ahead and fit the model so that we can look at some of the diagnostics we're interested in. Always make sure you select reference groups that make sense, because it's not just about fitting the model, it's also about the interpretation and the communication of the results. So here we have chronic cough never, marital status married, gender is female, race is white, activity level, I'm going to use the worst group as a reference group, so we're going to use inactive. Then we have exercise levels. I'm also going to use the worst group, which is little to none. And age, we're going to treat that as continuous per unit increase. Now we are going to estimate. We're going to focus the last day on exploring all of these features, confounding and collinearity. So we're going to save that for the last day. So now I'm just going to go ahead and click on estimate. So the platform takes the parameters we've supplied, the outcome and predictors, and now it's going to fit a Poisson model, which it has. So now we have the results here. This is are the variables in our independent variables. This is the categories we're comparing, and these are the results. A Poisson model produces incidence rate ratios. However, when we're analyzing a binary variable like 0 or 1 for prevalence, we interpret that in that context as prevalence ratios. So even though Poisson models will yield incidence rate ratios, when we're analyzing binary outcomes, we interpret those incidence rate ratios as prevalence ratios. That's just by the way. So how do we interpret this? So the p-values are here to tell you whether the results are statistically significant, but we can also judge that from a confidence interval. Since incidence rate ratios are ratios, it means that if the confidence intervals do not include 1, it means the result is statistically significant. So for example, this one, the lower limit is 0.96 and the upper limit is 1.01. That means that it does include 1. So that means that it is not statistically significant. But here we see that this is statistically significant. This is the category comparing underweight individuals to the normal individuals. We see that the IRR is 1.14 with confidence intervals ranging from 1.08 to 1.19. How do we interpret this? It means that the rate of cigarette consumption is 1.14 times higher among individuals who are underweight compared to those who are normal, and that result was statistically significant. We also see other results that were significant. For example, individuals who reported a chronic cough had 1.28 times higher rate of consumption of cigarettes compared to those who had never reported chronic cough, which makes sense. And so that's how we interpret the results. We also see a plot here that visualizes those exact same data in a more visual way that we can see. The platform also writes out the results so that we can be guided by it in case we don't know how to interpret the results by ourselves very well. And then very importantly, the metadata. This is where we want to really pay attention when we are using the regression models. It tells us a lot of things about the model. Metadata simply means the data behind the data. So that allows us to catch a high-level perspective of how or what went into the model. We can see that this is Poisson model. The outcome is smoke intensity. The denominator is the entire data set. We see here the full sample is 1,629. That's the number of rows in our data set. And since we did not subset our analysis, since the analysis was on the entire data set, the analyzed sample is equal to the full sample. However, if we had subset our analysis to a subgroup, then that will reflect, this analyzed sample will reflect that subgroup. And then here is the complete cases. These are individuals with data on all the variables we analyzed within our model. Then here we see indicators of model fit. I want to focus primarily here quickly on the variance to mean ratio. This computes the ratio of the variance to the mean. So we're looking at this, the illustration we saw earlier. We're saying when we compare the cover to the pot, is it roughly equal to 1? Because if there's equidispersion, we'll expect that the ratio of this to this will be roughly equal to 1. But we see from here that that ratio is not equal to 1 at all. In fact, the ratio is 6.7898. So there's clear evidence that we have overdispersion here, not equidispersion. So what we have is more of this than this. Now that suggests to us that in this case, a Poisson model might not be the best fit, and that we're better off with a negative binomial regression model. If we wanted to fit a negative binomial regression, we would simply come here and rerun the model. This time around, we will switch the model type from Poisson to negative binomial. We'll select our outcome, which is the number of cigarettes smoked or smoke intensity. And again, we'll select our reference groups, and then we'll run it again. The process will be exactly the same, and we can then evaluate the model fits and the figures as we did in the previous round. So that's how we fit a Poisson regression model and evaluate its performance on the chi-squares platform. I'll be sharing a data set and the instructions very shortly on LinkedIn. If you have any questions, you can drop them as usual on tag at chi-squares. Thank you very much.